today's video, we'll be talking about SN1 reaction. And so the first rule for an SN1 reaction is that the nucleophile is not important. So it does not need to be weak or strong. It can be both. And this will work for a tertiary carbon. So when you have one of these nucleophiles, it should come and attack the carbocation. The reason why it's not important is because this is first order, and so the rate law is rate equals K and the substrate, right? The substrate, and so the nucleophile is not in the problem, and so it does not affect the rate law. Our next rule, rule number 2, is that SN1 reaction must have a good leaving group, and so all these are actually good leaving groups, and so they should be on the structure when doing this, the mechanism for it. So these are all good leaving groups. So the third rule of SN1 reaction is that it will take place during a secondary and tertiary carbon. So for example, we have a secondary here, and then we have a tertiary here. Tertiary here. Now, it doesn't happen at primary or methyl because SN2 take place at primary and methyl. And we will talk more about secondary carbon. There's actually another process. So the fourth rule of an SN1 reaction is that polar Protic solvents will favor SN1 mechanism. So all of these right here, these are all polar Protic solvents, so butanol, propanol, ethanol, methanol, ammonia, acetic acid, and water. They will all favor an SN1 reaction. And also, when you use these solvents in a reaction, this reaction we call Solvolysis. Solvolysis just means these solvents, when using these polar Protic solvents, they will be acting as the nucleophile. They'll be used as the nucleophile. So that's all that means. And nothing happened. It's just the name of the reaction, and it's just the name of the reaction and nothing else. Just these solvents will act as the nucleophile, just as how like bromine, iodide, chlorine, how they act as a nucleophile. Negatively charged. The fifth rule for SN1 reaction is that it can occur. A carbocation rearrangement can occur. And so for this, a hydride shift and a methyl shift can happen. So for example, if we have this structure, this carbon right here, we see that is a tertiary carbon, right? It's connected to 3 other carbons, 1, 2, and 3. And so let's say that, for example, the positive charge was on this carbon over here. So this carbon over here, tertiary carbon, has a hydrogen, and so this hydrogen will go to that carbocation, and so we would have this happen, and the positive charge would be over here. So this is a hydride shift. Hydride shift. Okay, so now it can also happen a methyl shift. So for example, if I had some sort of this structure, okay, and methyl shift only happens when there's no hydrogen, and so this carbon would be connected to 4 other carbons. So that's 1, 2, 3, and 4. So a methyl shift would happen here. Methyl shift only moves a methyl group. So for this case, if we had the positive charge over here on a secondary carbon, we can move to a methyl shift over here. And so we would get a result something like this. Okay, methyl shift will move over here. We still have this over here, and the positive charge will go over here. And so this is called a methyl shift. And so when doing the mechanism for an SN1 reaction, hydride and methyl shift can take place for the molecule to be more stable. The sixth rule for an SN1 reaction is that we will have a racemic mixture for the products if that carbon is a chiral center. So for example, if I had this structure and iodide was the leaving group, And this is reacting with NaBr. We know that Br is the nucleophile, so we would just draw the answer like this. Because this carbon over here is a chiral center, so we would have the bromine on here, and plus the racemic mixture, the other one, 50% wedge and 50% dash, and so like this. Remember back for SN2, it was an inversion where we only had one product, but for SN1, it will always be a racemic mixture if that carbon is a chiral center, so in fact we will have two answers. And for an SN1 reaction, for the seventh rule, when doing the mechanism, it can attack from any side. So, for example, if we had the carbocation over here, and let's say our nucleophile was bromine, okay, and then it can either go from the front or it can go from the back. It doesn't matter. For SN2, you can only pick one side. It usually goes from the back side, but for SN1, it can either go the back or the front side. And that is why we get two products instead of one. So now let's do an example for it. So if we have the structure, and let's say the iodide, and this was reacting with NaBr. So how do we determine if this is an SN1 reaction? All we do is look at the carbon that is attached to the leaving group, this carbon right here. And so we know that this carbon is connected to 1, 2, and 3 carbons. So this makes it tertiary, and SN1 always happens at a tertiary carbon. So from here, all we do, no need for carbocation rearrangement, no need for methyl hydride shift, because it's tertiary. This is the most stable. This is all we want. So if we have this, all you do is just substitute the nucleophile for the leaving group. So substitute the Br for the iodide. And so this is our answer. And then plus the iodide as a byproduct, like a chart. Okay, so this is how you do the product. Okay, now if we want to do the mechanism for it, how do we get this answer? Let's go back. Start from the structure. The first step for this is the leaving group leaves. Okay, so the leaving group leaves, give off the electron, so we have something like this. Carbocation, right? We had made the iodide, negative charge. So now the nucleophile comes, the Br, bromine, right? The sodium is a spectral ion, it doesn't do anything. Bromine is a very good nucleophile for this. Okay, so we start from a lone pair and it can attack from the back or it can attack from the front. It doesn't matter. All that matters is that you attack from one side and you will get two products. Well, actually, for this case, one. Okay, Br. The byproduct was iodide, the negative charge. Negative charge, and this is our answer. There is no racemic mixture because the carbon in the middle is not a chiral center. So no racemic mixture for this, so one product. Let's do another example if we have the structure right here. So let's say this is a bromine, and this is reacting with, let's say, NaI, sodium iodide. And so for this, we see that the carbon that attached to the leaving group over here, it is tertiary because it is connected to 1, 2, and 3 carbons. So for this is tertiary, this is the most stable, so we don't really need to do no carbon-cation rearrangement. So all we do is just substitute the bromine, the iodide for bromine, and so we would have this as the product without even doing the mechanism. It is the same thing as SN2. Okay, this is for tertiary. Now let's do the mechanism for this. And so for this, if we have starting like this, always the leaving group leaves. Okay, it's a one-step arrow, and so we would have this right here, and then we would have a carbocation over here. Since the carbocation is tertiary on that carbon that is tertiary, No need for methyl or hydride shift. It is the most stable that it can be. Now the nucleophile comes in, iodide. Okay. By the way, we actually made the byproduct. Br is floating. Has a negative charge. Now we make the iodide comes in as the nucleophile. Comes and attack any side. When it does this, we get an answer like this. Iodide. Also remember that this carbon, it is a chiral center, so a racemic mixture comes in play. So we would have this 50% wedge plus 50% dash. Well, actually, matter of fact, change the methyl group. Okay. Methyl group will have the dash. Let's have the wedge on the iodide. Let's have the wedge on the methyl group, and now the dash on the iodide. Okay, this is our answer for this. And also the Br as the byproduct that we have made. The byproduct is not really important, but the racemic mixture is. Racemic mixtures. Let's do another set of problems. So if we have this structure, and let's say we had a Br bromine on here, say it's an alkene, it's a methyl group right here. And so this was reacting with, let's say our reagent was CH3OH. So this is methanol. And so let's say it was actually 20 degrees. SN1 can actually happen in cold temperature, so something like this, 20 degrees Celsius. So if we're only doing the products, not the mechanism, not just yet, we look at the carbon attached to the leaving group right here, this carbon. This carbon is attached to 3 carbons, 1, 2, and 3 carbons, so that's tertiary. So no need to do carbocation rearrangement, no methyl shift, no hydride shift. And so when we do the products, it'll be like SN2, where we just redraw the molecule. And instead of putting the Br, all we would do is put the OCH3. Okay, and I'll show you how we got here. Okay, so this is the answer for it. Now this is the mechanism for this. First things first, always an SN1 reaction. When we have an SN1 reaction, we know there's an SN1 because it's tertiary also. But also now we look at the reagent that we have, right? It's methanol. Methanol is a polar protic solvent. When we have a solvent as the nucleophile, we call this reaction Solvolysis, right? Solvolysis reaction. And all it means is that the solvent, the polar protic solvent, acts as the nucleophile. So nothing really changes. That's just the name of it. Okay. So first step is that the leaving group leaves. That's always the first step of an SN1 reaction. We redraw the structure, we keep the alkene. Okay. Now there's a carbocation right there. Okay. So now we use our reagent, which was CH3OH methanol. Right. So CH3. Oxygen has 2 lone pairs. It goes and attacks the carbon that has the carbocation. So from here we redraw the structure. Still an alkene. So from here we would have this. That's just the hydrogen, and then we have the CH3. Now from here, as oxygen has 1 lone pair and a positive charge. We can't stop here because we do not want to have a positive charge in our reaction. So we use our reagent again. We have the polar protic solvent, the methanol. So methanol comes again. Comes again. And actually this oxygen goes and grabs that hydrogen. This hydrogen gives off an electron to oxygen. And so we would have a final reaction of something looking like this. Okay, the hydrogen is gone. All we have is the CH3, right? And then actually plus the byproduct that we had made. Positive plus, positive charge. It's our final answer for this. There is no racemic mixture because this carbon right here is not a chiral center, so no racemic mixture. That's the answer for this problem. Now, let's do another problem. So if we have the structure, okay, and let's say bromine was on here, and this was reacting with H2O, water. So water is a polar Protic solvent. Just to let me know this is an SN1 reaction, but also this carbon right here is a secondary carbon, right? It is connected to 1 and 2 carbons, okay? So now this is where a carbocation rearrangement will happen because we want to put the bromine, well, not the bromine, but the nucleophile on the carbon that is tertiary. So in this case, we look for a carbon that is tertiary, and we see that this carbon is a tertiary carbon. So if we're only doing the products for this, we would actually move the bromine from a secondary carbon to a tertiary carbon, so something like this, OH. Okay. As a matter of fact, that carbon is a chiral center, so it would actually have a wedge, have 50% wedge, and 50% would have a dash, so something like this. Okay, this is just doing the product of it. Now let's do the mechanism and how do you get these products. So we start with this, and the first thing we do for SN1 reaction is the leaving group leaves. Okay, so let's do that. Redraw the structure. We have this, and the carbocation is on this carbon. This carbon right here is secondary carbon. We want tertiary because tertiary is the most stable. So this is the carbon that is tertiary. As a matter of fact, this tertiary carbon has a hydrogen. So we do a hydride shift. So this hydrogen goes electrons to that carbon that has a positive charge. So then we would get a having the positive charge on that carbon now. Now from here, we bring our reagent, which is water. Okay, water comes in, attacks from any side, let's say the back, goes here. Now we would have a structure that would look like this. H. Now this oxygen has a positive charge. We do not want this, so we bring water again to deprotonate that positive charge. So water comes again. Oxygen low pairs go to the hydrogen, and hydrogen gives off the electrons to that oxygen to form OH. So from here, we get something like this. Again, this is a racemic mixture, so 50% wedge and 50% dash OH. Plus the racemic mixture. But also, let's not forget the byproduct. It's not really important, but you can write it if you want. And so this is our final answer for this problem. Alright, let's do another problem here. We have the structure over here like this, and we had chlorine. This is reacting with, let's say, methanol, so CH3OH. And so from here, we see that this carbon, let's see if this is a secondary tertiary, so we have a secondary carbon here. So in this case, we have a secondary carbon. We know this is SN1 because we can see that the reagent is a polar Protic solvent. So that gives us this an SN1 reaction, okay? Now the product for this. When we do the product, we actually want to have a rearrangement because this carbon is connected to 1, 2 carbons, making it secondary, okay? we actually want something that is more stable. So we look around if we see tertiary carbon. Okay, you don't see a tertiary carbon at all, but we do see something that has 4 carbons connected to it, which is this carbon over here. This carbon is connected to 1, 2, 3, and 4. We have 1 carbon that is connected to 4 carbons. We have a methyl shift here. Okay, so there was a carbocation rearrangement. So let's move the chlorine, the OCH3 over here on this carbon. So then our product will look like this. Another way around. But this is our final product for this methyl group. Okay, so now what I'm going to do the mechanism for this. So the mechanism. So first things first, that we know that the leaving group has to leave. And that happens. So we redraw the structure exactly the same. The leaving group has left, and we have a positive charge here. So we look for this carbon, as we know, is a secondary carbon. So let's move it to somewhere where it can be more stable. So we don't see a tertiary, but we see something that is quaternary, where it has 4 carbons connected to each other. So that will be this carbon. So there is no hydrogen on this carbon, but there is a methyl group. So let's actually do a methyl shift. So we can actually do something like this. It doesn't matter which methyl group you use here, but I'm going to use this one right here. So it goes and moves on that carbocation. So we get a structure that looks like this. Okay, 1 methyl group here, methyl group 1 over here, and then there's a carbocation over here. Now, CH3OH comes in, so the methanol comes in. Okay, oxygen goes and attacks the carbocation from any side. Okay, now this will give us a result of something like this. Actually, no, it doesn't have 2 lone pairs, but it has 1. It has 1 lone pair. It has a positive charge. Okay, now to be part of this positive charge, we bring methanol again. So CH3OH, oxygen lone pair go to hydrogen. Hydrogen gives off the electrons to that oxygen. Okay, let me make that better. Something like that. Okay, now for the structure, all we have to do is redraw it. And this is our final answer, and also the chlorine that is our byproduct in the answer. There is no racemic mixture because this is not a chiral center. So that's our answer. So now let's do another example. If we had this structure, and our reagents for this was, let's say H3O plus, and then we have methanol. Okay, now for this, we have to determine if this is SN1. So as we can see that the leaving group, the carbon that has attached the leaving group is attached to 2 carbons. We got 1 and 2 carbons over here. So this is a secondary carbon. But now we look at our reagents. We have a CH3O plus OH. This is a methanol, which is a polar protic solvent. So this will take a Solvolysis reaction as of our polar protic using as the nucleophile. For this, our first step for SN1 reaction is that the leaving group leaves. This is not the case for this problem because OH is a bad leaving group. So now we can't do this. This mechanism that will take place will be only for SN1 reaction, and this is only for OH hydroxide. So again, this is only for an OH group that is a leaving group, and this is for when we're performing an SN1 reaction mechanism. So our first step will not be the leaving group leaves, not yet. Hydronium comes in. H3O+, it comes in with 3 hydrogens. It's a positive charge, okay? One of oxygen's lone pair on the OH goes and grabs that hydrogen. Now this hydrogen gives off an electron to this oxygen, and so we would get a reaction that would look like this. Now we have 2 hydrogens on this oxygen that would have a positive charge, structure like this. From here, we can now actually leave the leaving group. So the leaving group leaves, we kick that out, and so we would get a reaction like this. Positive charge right here. Okay, now we ask ourselves, this carbon over here is secondary. Can we make it more stable, either tertiary or have a carbon that's connected to 4 carbons? So in this case, we do have a tertiary carbon that is down here. Okay, it's connected to 1, 2, and 3 carbons over here. So this in fact has a hydrogen, right? We call this a hydride shift. Again, this hydrogen goes and grabs that, attacks the carbon with the positive charge. And so this will give us a reaction of now having this carbocation on this tertiary carbon. Okay. Now after this step, we see that we have to bring in our second reagent, which is methanol. So methanol comes in. CH3OH, 2 lone pairs on oxygen. Oxygen, hydrogen, the oxygen lone pair goes and attacks the carbon with a positive charge. Doesn't matter which side, and it will give us a product that will look like this. CH3, this oxygen has a positive charge. Now we cannot leave this here. We must now bring in something to deprotonate it. So we still had our water as the byproduct that we made over here. In this step, we had made water. So over here it would have H2. Water was made over here. Okay. We bring that into our reaction. So water comes in to deprotonate this oxygen. One lone pair goes to hydrogen. This hydrogen gives off the electrons to oxygen. And so we get a final product of looking something like this. And also plus the hydronium that we have made. So this is our final answer for this problem. No racemic mixture, no chiral center, so no racemic mixture. This is because we see a 1, 2, and 1, 2 ethyl on both sides. So now let's work on another reaction here. So if we have this structure, this time we have another OH group. So we have 2 methyl groups on the side, and then we have this extra methyl group on here. And this was reacting with our reagents. First one will be H3O+, hydronium. Second reagent will be, let's say, ethanol instead. Ethanol, okay? Now the first step, as usual, for an SN1 reaction. So we know that this carbon is secondary. So we look at the products and the reagents. We have a polar Protic solvent, so this means we'll be taking a Solvolysis reaction, meaning the solvent will be the nucleophile. So in this case, with this SN1 reaction, we know that the leaving group leaves, but as I said again, OH are a bad leaving group. So OH is a bad leaving group, and so it cannot leave first. So now we have to use hydronium to remove it. So let's use no space here. So let's write with three hydrogens here. Now one of the lone pairs on the oxygen goes and it grabs that hydrogen. This hydrogen gives off electrons to oxygen. When it does this, we get a reaction that will form like this. So now we have this, and now this oxygen is connected to two hydrogens with one lone pair with a positive charge. Now we are able to kick it off. Leaving group leaves, and so we get a reaction of this. Okay, so the methyl group's here. When you kick it off, we have a positive charge. Now, we see that we need to do something. We see if there's any tertiary or any carbon that has carbon that is connected to four carbons. So here we see that there is actually, we can do a hydride shift, but also we can also do a methyl shift. But we can't do both. We must pick one. In this case, a hydride shift is much faster than an alkyl shift. So a methyl shift. So that's why we use a hydride shift instead. Now we have this reaction over here. Now the positive charge go on this a tertiary carbon. Now from this, we would actually bring out our ethanol. Will come in, our second reagent. Oxygen has two lone pairs. It goes and attacks the carbon with a positive charge. Now we have a formation of this. Oxygen, the hydrogen, and now the ethanol. Okay, this has a positive charge. We know to remove the positive charge. We can use water, as we made, at this step right here. We had water on our second step. We can use water, or we can use another ethanol. It doesn't really matter at this point. Well, the ethanol would work because it outnumber the water, but it'll still give you the same result. So in this case, I'm just going to use ethanol. We can use water. Okay. Let's deprotonate this oxygen. So it goes and grabs the hydrogen. Right there with the red. Oxygen lone pair goes and grabs the hydrogen. This hydrogen gives off the electron to that oxygen. And so we would have a final product looking like this. We know that this carbon is a chiral center, so we must have racemic mixture. Okay, let me actually erase that part. The methyl group should have a wedge. If this has a dash, it's just if they had the ethanol has the wedge. Plus the other one has a dash. Oxygen has two lone pairs in this case, and this is our final product for this problem. Let's see, racemic mixture, ethanol. Okay, let's do another problem now. We have this structure, and then we have an alkene this time, okay? And this is reacted with, let's say, with methanol actually. And so our leaving group would be with bromine. Okay, so again, as you can see, the carbon over here is a secondary carbon. It's attached to two other carbons on to the left and on the right. And so also we also note that this right here, it is a polar protic solvent. So this makes it a Solvolysis reaction, meaning the solvent is the nucleophile. So Br is a good leaving group. The Br leaves, right? That's our first step as SN1 reaction, always. We redraw the structure. Br has left and the carbocation has formed here. Now the carbocation can actually look at other places to see if there is any tertiary or a carbon that has 4 carbons that it can do a methyl or hydride shift. In this case, there is actually no methyl and hydride shift because we have a double bond here, right? So now, to get the result, to get this on a carbon that is more, more stable and whatnot, we can actually do resonance. Now, on this point, we start from the double bond and it actually goes towards the positive charge because that's one of the rules of resonance. So we have this happening. So when this happens, what arrow? 2 arrows now. Okay, we would have something like this. Now the double bond will go over here. The positive charge will move 2 places, and so it would be on this carbon over here because they went 1 and 2 on the second. Now from here we see that it is more stable than having on the secondary carbon because we have it on the tertiary carbon. Now from this step we actually bring in the ethanol. Ethanol comes in. Oxygen has 2 lone pairs, and one of the lone pairs goes and attacks the carbocation. And so from this we get a reaction of oxygen here with 1 lone pair, the hydrogen here, and then we have the methyl, CH3. Now from here, oxygen has a positive charge. Now, to remove this positive charge, we must bring another methanol. So we have the CH3OH. The oxygen goes and grabs the hydrogen. The hydrogen gives off the electrons to the oxygen. And so from here we get a final product of OH3, OCH3, plus the double bond here. And so this is our final product. No need for receiving mixture. By the way, when you do resonance, put the bracket where you have done resonance, shown resonance. So this is our final product. We also have the byproduct. Positive charge. It's not that important, but it's good to add it to the problem when you're doing the mechanism. And so these are our final products for this problem.